And I know I'm starting maybe 5 minutes late, but I'm hoping to get through this part. We'll see. I'll go ahead and tell you though, it says it, I added to this slide that if you have your assignment sheet, which remember this is my, I dream about the ones I still have to do. For actually 7, 8, and 9, they're not due until after we do the lab on Thursday. So even if we do get through this part 7 won't be due until the following Monday. So Thursday lab, due on Monday. That gives me time. So when we talked about ionic compounds, we said metals lose electrons to get an octet, non-metals gain electrons to become anions and get a complete octet. Well, this idea of electrons being shared is what's up with non-ionic bond, a covalent bond. Now, the other day when we had kind of two things, and hopefully you kind of got that in your notes, where this one was molecular compounds. A synonym for molecular compound is a covalent compound. This other column was ionic compounds. We kind of talked about these are molecules, these are formula units. Okay, so molecular compounds, covalent compounds, if you look at how the atoms are joined together in that repeating unit, of course we call that repeating unit a molecule, all of those bonds are going to be covalent bonds, where electrons are shared in all cases. So again, I know it's not up here, but it is in my mind. So this is molecular covalent compounds, this is ionic compounds. So when we talked about kind of the nature, we talked about electronegativity. Remember, that's kind of like the tug of war between two atoms. And we said that if electronegativity is high enough, the nonmetal actually will abscond onto an electron, and the metal will lose an electron, then you have an anion and a cation. Then you have what I call a dot, 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 an ionic bond. Well, we said over here, again, okay, my invisible covalent compounds, molecular compounds, we said that these are nonmetals bonded to other nonmetals, okay? And the thing there is if you look at the electronegativities of the two atoms that are joined together, they're not strong enough for an electron to be transferred, so electrons are going to be shared. So it's all about the electronegativity and electronegativity difference. So again, we talked about the Greek letter chi, which looks like a funky X. That's the electronegativity value. The electronegativity value is a want for an atom to get the electrons as it's bonded to another atom. So hopefully you recognize the JAG. Here's the JAG here, separating the metals from the nonmetals. So when we're talking about molecular compounds, covalent compounds, we're just talking about these atoms bonding together to make compounds. And you're like, well, that's not very many atoms to choose from to bond together to make a compound. But those are going to be your covalent or your molecular compounds. There are a few exceptions. But if you join any two, then the electronegativity difference isn't great enough for an electron to be transferred. Those lines, and we will be talking about this on Thursday, is the periodic trend for electronegativity. So electronegativity increases across the period, and electronegativity increases up the group. So we kind of have that sort of thing, electronegativity, or the chi value. So when we talked about metals forming cations and nonmetals forming anions, it was to get a complete octet, to get like those rare gases over there. So we're going to actually continue that theme when we talk about electrons being shared. I'm going to go ahead and pick on water. And I'm going to draw the first kind of sort of Lewis structure. Thursday, we're going to draw Lewis structures of molecular compounds. We're also going to draw Lewis structures of those polyatomic ions. You've been memorizing like nitrate and that sort of thing. But of course, the formula for water, you would tell me, is H2O. So if we want to draw the structure of water, we need to account for the 2 hydrogens and the 1 oxygen. So one of the things that we do a lot in drawing structures is to actually go back and say, how many valence electrons does that atom, that type of element have? I don't know if you remember, but if it's a group A element, which hydrogen and oxygen are, you can look at their group number and you have number of valence electrons. So I'm just going to put a 1 valence electron up here because hydrogen's atomic number 1. If it's neutral, it has 1 electron. So there's my 1 valence electron. Oxygen, again, I'm going to bring a Sharpie one of these days, and above oxygen, sulfur, selenium, tellurium, I'm going to put 6A. So that oxygen has 6 valence electrons. So let me kind of show you what an oxygen atom, what a water molecule looks like. I'm going to go ahead and for the oxygen, I'm going to make those 6 valence electrons X's. So here we go. X, X. Let's see, should I do it this way? I'll do it this way. X, 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 X. It's like a magician now. Keep me honest here. I'm liking 6 for that. Right? 6 valence electrons. Hydrogens, I got 2 of them. I'm going to saddle them in the west position, and I'm going to saddle it up in the east position. They each have 1 electron, and I'm going to go ahead and instead of an X, I'm going to make that a circle. So there's my 3 atoms joined together in a water molecule. Let no man put us under. Sorry. All right, there's a water molecule. Now, what we do with Lewis structures, anytime we have electrons like this, 2 electrons, we're going to see a pair of electrons connected. A pair of electrons make what we call a covalent bond. So I'm going to rewrite this structure. Here's my oxygen in the middle. Instead of this 2 electrons, I'm going to put 1 dash. I'm going to put my H. Instead of those 2 electrons, 1 dash, my H. And then I still have to, I'll go ahead and turn them into circles because we usually use little dots as the extra electrons. So that's actually kind of what I call the final Lewis structure of water. So when this slide talks about double dipping, I can switch colors here because I have other colors here. See how green works for us. It's like drawing a Venn diagram or a shared custody. So anytime on a Lewis structure you see 1 dash, you're going to have to translate that to a pair of electrons. So I'm going to draw a little circle around that hydrogen atom. I'm going to include all electrons it has at least joint custody over. And I'm going to draw a circle around my oxygen atom. Now that gets exciting because now we have, this is the shared electrons right there. The crossover, the double dipping. I'm going to go ahead and address this one on the east. Okay. And that almost looks like a hat. But anyway, so there's my water molecule. So it's about octets. So can you see where this guy right here, the circle around the oxygen, I have 2 electrons there, plus 2 that makes 4, plus 2 that makes 6, plus 2 that makes 8. So that is the complete octet. Octet around my oxygen atom. All right, double dipping. That's what happens when you share electrons. So it's all about the octet. There are a couple of exceptions. Well, I don't think I have it on the slide, but it's how many electrons does this hydrogen atom have at least joint custody over? 2. So hydrogen never wants to have 8. It wants to have 2. But what rare gas has 2 electrons? Unlike in helium. So it has rare gas configuration. So most atoms want to have 8. Boron wants to have 6. I don't know why boron does that. But when you draw a Lewis structure for boron, you'll see it has one of the final Lewis structures will have custody of 6. And in your homework, not on the test, but in your homework, now check out the criteria for this. Any element from period 3 or greater. All right, let's find period 3 on here. So of course, these are the numbers for the periods. So anything that's greater than argon or whatever, you're like, are you serious? That's like almost all the elements. If you read that, it says that any of these elements is possible, and it really happens in the transition elements especially. The final Lewis structure won't have 8, it'll either have 10 or 12. So they kind of go in pairs. So 8, 10, and 12. It's what we call an expanded valence. Okay. So for expanded valences, you're going to look for, instead of 8, you're going to see either 10 electrons or 12 electrons around the final when you draw the Lewis structure. So those are 3 exceptions: hydrogen 2 electrons, boron 6 electrons, and expanded valences. All right. So earlier we talked about electron configurations. Even before that, we talked about quantum mechanics, like electrons can be S-type, P-type, E-type, or F-type. We actually use the term orbital, electron orbitals. So here on the slide, when it's talking about atomic orbitals, I think of it like this. Okay, this is the nucleus of atom A. It's adorable. This is the nucleus of atom B. And of course, around the nucleus, we have electrons. So what type of orbital is dumbbell shaped? It is P, yep. So if you want atom A and atom B to join in a covalent bond like this, okay, what's going to happen is, and I'll pick on P because they just look cool. Okay, there is an atomic orbital of of A, and I'm gonna have to stretch this one. This would be humongous. Can you see the overlap? Okay, so these kind of lobes are atomic orbitals. Atomic O for orbitals. This right here is a bond orbital. It's the overlap of 2 atomic orbitals. Or like I said, kind of the center there are the nuclei. Now, it's possible, depending upon the nature of the atoms that are involved, that you'll have more of an overlap for a stronger bond, more energy to break that bond. These are covalent bonds. Or kind of a less overlap, and it'll be easier to break. So there's definitely not all bonds, covalent bonds, are created equal. So that overlap. So when I talk about a bond orbital, I'm going to kind of redraw my water molecule. Here's my water molecule. We have a central oxygen atom, covalent bond, hydrogen, covalent bond, hydrogen, and these are, we're going to I'm going to put a name to those extra electrons coming up. But anytime you see this on a Lewis structure, think of it as, okay, covalent bond, and then actually we have 2 electrons that are shared to make that happen. So a minute ago when you saw the nuclei of A and the nuclei of B and the overlap of the 2 atomic orbitals, think of that bond orbital where 2 electrons are right there. Right there. That's cool. And though they have to have opposite spins. In this case, I kind of picked on water on purpose. In this case, I kind of identified of the 2 electrons that are being shared to make that covalent bond, 1 electron comes from the hydrogen, 1 comes from the oxygen. That doesn't have to be that way. Okay? In this case, sometimes they actually, both electrons that exist in that bond orbital came from the same atom. Okay, so in covalent bonds, electrons are shared in pairs, 2 electrons, 2 electrons. So I'm going to draw some structures over here that I'm going to refer to later. So these are final Lewis structures. We're going to pick on C2H6, and it looks like this. What you do is you usually draw the carbons in the carbon chain. simply have a carbon, single bond, carbon, and then my 6 hydrogens, I've got 3 hydrogens over here and 3 hydrogens over here. Sometimes when you're like drawing, this is just called we call a hydrocarbon. You get lazy and you don't even put the H's there, but I'll go ahead and put the H's there. I got 6, 3 here. Now each one of those dashes is a pair of electrons, 2 electrons. So if I drew a circle around this carbon, you'd see it has 8 custody of 8 electrons. Around this carbon, again, 8 electrons. Each one of those bonds is a single bond. All right, double bonds. I'm going to stick with hydrocarbons. I'm going to show you the formula of this is C2H4. So double bond, you've probably seen these before. I'm going to draw the carbon skeleton of those 2 carbons. Carbon, double bond, carbon. And then each carbon has 2 hydrogens. So I'll keep them up like that, kind of an angle. Hydrogen, 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 hydrogen. Okay? So this right here, this is called a double bond. Double bond. The last one is a triple bond. And an example of that hydrocarbon would simply be C2H2. So now between my 2 carbons, I'm going to put carbon, dash, 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 carbon. Each carbon gets 1 hydrogen. And this is actually a hot dog shape. I like the shapes. So this collectively is called triple bond. So just based upon, now I'm going to ask you guys a question, just based upon what we talked about, how many electrons are there here in this single bond? 2. Yep. How many electrons here in this double bond? There are 4. I have 2 for this one and 2 for this one. So there are often 4 electrons here. How about the triple bond? 6. Yep. Exactly. Cool. Kind of. Lindsay's asking, is it because I need to have 8 around them? And yeah. Because if I were to draw, and I'll go ahead and draw a circle, like a little Venn diagram, I'll pick on that, I'll pick on the left carbon. If I do that, I have 2, 4, 6, 8, or I have 6, 7, 8. I have a complete octet, like that, exactly. And I can do the same with the other carbon. So now with these dashes, anytime you see a dash on a Lewis structure, a solid line anyway, solid line on a Lewis structure, that means 2 electrons are being shared with each line. We have 2 types of covalent bonds. I kind of call them vanilla and chocolate, kind of, a little bit. Probably better put, there's the main course covalent bond, and then there's the follow-up. There's like actually dessert, pie type desserts with a lot. So this right here, the circle with the little tail, is the Greek letter sigma. It's a lowercase sigma. The uppercase sigma looks like E, like summation. This is the lowercase sigma. So sigma bond. Sigma bonds, and I was going to add to my slide, I usually say they are the first to arrive. The word primary kind of gives it away, but first to arrive. Okay. 2 atoms are covalently bonded. Okay. If 2 atoms are covalently bonded, then there has to be a primary or sigma bond. It has to be. In this first structure up here, you would tell me that all of these are single bonds. So here we have a sigma, 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 sigma. Right? If 2 atoms are doubly bonded, so that moves down to the C2H4, right here, only one of them is sigma. Okay, the other one is dessert. The other one's on the next slide called hot. So I usually pick the top one. I say that's the first to arrive. That is my sigma bond. With a triple, down here, my first to arrive, and it could be any of them, but that is my sigma bond. Okay. Now I brought, actually, I have those three structures here. This one is C2H6. So 2 carbons, 3 hydrogens, 3 hydrogens. And the gray actually in these models I have represents the sigma bonds. So 2 electrons, 2 electrons, 2 electrons, 2 electrons, 2 electrons, 2 electrons, 2 electrons. The last part here says that with a sigma bond, you picture those, the bond pair electrons lying in a path between the nuclei of the atoms being connected. Okay, that's the 2 carbons. We could go like this for the carbon-hydrogen, 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 right? Well, I almost get nostalgic when I get to this part, because the secondary bond, of course, that's the Greek letter pi, right? The Greek letter pi. So we call these pi bonds, and I think it's funny because they're like desserts. They're secondary bonds. Okay. So it goes like this. If you have a single bond, okay, it's sigma. If you have a double bond, the first to arrive is sigma, the second one is pi. So sigma, I'll go here, I'll go pi bond. If you have a triple bond, you have sigma, pi, pi. Pi bonds. That's how that works. Oh, I didn't finish that thought. So the nostalgic part comes in. My grandma passed away years ago, but she loved pie. She would go in the restaurant, and the first thing she wanted was the pie. Can you bring me a menu for your pie? I'm like, oh, grandma, I'll take one of each. So I'll have this first. Okay. So the other models I have are for the C2H4 and the C2H2. Okay, so this is the C2H4. So the grays are sigma, they're the first to arrive. And if you look at, if you compare these two, you can see with regard to the hydrogens, we have single bonds. So of course, you can see the carbon sigma bond, carbon sigma bond. The thing about the pi bonds is they can't, those pair of electrons that are for that secondary bond, they can't hang out here because that's taken with the sigma bond electrons. So what they do actually is they hang out kind of in a sandwich, above and below or outside. So electrons are a funny thing. They buzz around so like that. Okay, they actually create a cloud here, here. Isn't that cool? Okay, so that's a double bond. Sigma, pi. Right? So triple bond looks like this. So again, so this is C2H2. So again, if we look here, we're looking at the sigma bond. Sigma bond. There's the sigma bond between the 2 carbons. But since it's a triple bond, you actually now have 2 pi bonds. So pi, pi. But anyway, one pair is 2 electrons for the pi bond, another pair, 2 electrons for the pi bond. Isn't that cool? But so those bonding electrons lie outside the region for the sigma bonds, primary bonds. So pi bonds are sometimes they're dessert, they're called secondary bonds, the second to arrive. All right, so here's some Lewis structures. Lewis structure of HCl. Notice that, and you're going to want to be able to do this on a Lewis structure for your next unit exam, which is going to be here before you know it. It's a week from Thursday, right? Your next unit exam, I'm going to give you a Lewis structure and ask you questions about it. So hopefully you would say, we have 1 sigma bond. Okay. The caption for this is the O2 molecule. Notice we have a double bond is always going to be sigma pi. Okay. And then we'll go back to like what Lindsay was saying. Do you see where if I wanted to, on this final Lewis structure, draw a circle around this left oxygen, does it have a complete octet? Yep. What this one? Complete octet. Yep. Well, we need to get a triple bond in there. Molecular nitrogen. Most of the gas in this room looks like this. I just think it's so cool because, like, if you're unsavvy, you're like, oh, N-N. No, it's N-N, right? So how many electrons are there in this triple bond? 6. Yep. So if there's 6 there, yep, 2 plus 6 is 8. 2 plus 6 is 8. Cool. Well, this is where I almost wish they had a different word for this. It's called, and I call it, you'll hear me call it Thursday's lab, I call it the expected valence of an atom. Sometimes I call it then, let's see, expected valence of an atom, total number of covalent bonds. Okay, and sometimes I'll call it reaching out, because I just reaching out from an atom. The other problem about this sort of check, the expected valence of an atom reaching out as it's bonded to other atoms in a neutral molecule. There's so many catches with this. Neutral molecule. And I'll remind you of this on Thursday. But this idea of the expected valence of an atom, it only applies to Lewis structures where it's a neutral molecule. And I already mentioned that sometimes Thursday's lab you're going to be like drawing a Lewis structure of nitrate, like NO3 minus 1. And stuff like that. So, how many times do you expect it to reach out in a neutral molecule? It is 8 minus the group number. 8 minus the group number. Oish. So let's check this. 8 minus the group number. So what's the group number of oxygen? 6. Like 6A up here. So it's 6A. So 8 minus 6 is 2. So here for the water molecule, when I talk about reaching out, now that reaching out in this case is sigma and pi bonds. Okay, I have 2 sigma bonds. That's perfect. Okay, what group is carbon in? 4A. Yep. 1, 2, 3, 4. 4A up here. I need to add those. So 4A. So 8 minus 4 is 4. So sigma and pi bonds you expect is 4 in a neutral molecule. So if we go over here, how many sigma bonds around the carbon? 4. Yep. 4. No pi bonds. So sigma plus pi is 4. All right. How about this guy? How many sigma bonds? Fingers. Sigma bonds. I'm liking 3. Yep. Sigma, sigma, sigma. Cool. And then how many pi bonds? 1. So 3 plus 1 is 4. Reaching out 4 times. How about down here? How many sigma bonds? Fingers. Those. So 2 sigma bonds. How many pi bonds? 2. So 2 plus 2 is 4. So it's reaching out 4 times. Well, you know that boron is irritating. So, of course, boron doesn't follow the rule. How many electrons does boron want around the Lewis structure? It's not in the phenol Lewis structure. It's not 8, it's 6. If they're going in pairs, that means it's probably going to reach out 3 times. And hydrogen only wants to reach out once. Now, I hope this happens even to the best of us. Sometimes I'll be looking at people's Lewis structures, and they will load up that hydrogen with extra electrons, but it only wants to reach out once. It wants to be like heat. So this, if you were to find these are all nonmetals, forming these covalent bonds with other nonmetals. So if you were to find the groups, of course, 4 came from 8, sorry, this is, you guys told me Roman numerals the other day. Okay, so if you take 8 minus 4, if you take 8 minus 5, 8 minus 6, 8 minus 7, okay, and these guys, they just are like that. What about the rare gases? Okay. How many times do you expect that to reach out? So follow the rule. So what group are they? They are 8A, so 0. It's true. So 8 minus 8 is 0. They're inert. They don't like to reach out. They have arrived. I think we talked about these Lewis electron dot formulas, and it looks something kind of like this, where if you go across, we have 4A, 5A, 6A, 7A, and 8A. So basically you're looking, those little dots are the valence electrons. Around the atom, valence electrons are most special. And then the the symbol kind of then represents the nucleus of the atom and the non-valence electrons. What this says is, and I kind of picture a little kid playing with cars. And if you figure you have a garage that has, now there is no significance. I'm going to put an N here for north, south, east, and west. It really doesn't matter. That's one of the things I have coming up. There really is no north, south, east, and west to Lewis structure. But I think of a garage that has like our central garage with 4 compartments, and it can have 2 cars in each. So back to a little kid playing with cars. So the expected valence of a 4A nonmetal like carbon is 8 minus 4, 4. So here we go. Drive a car there. So there's kind of the reaching out. Nitrogen, it already has 5 valence electrons, so it has room for 3 things to park. Oxygen has room for 2 things to park. The halogens has room for 1 thing to park. And of course, the rare gases are full. I'm just really entertaining myself. So we're going to look at some Lewis structures, and we're going to play a little game where, and this is the first step in drawing a Lewis structure, the atoms involved in the structure kind of take their valence electrons, they throw them in a pot, and then those electrons are those pot of valence electrons are distributed on the Lewis structure. Now, when electrons are distributed, and I'll show you what I mean. Let's just pretend right here. So when we talked about water, this would be a good example. Up here, I put the number 1 over the hydrogen, and I put the 6 over the oxygen because it was 1 valence electron, 6 valence electrons. So we're going to call it the pot of valence electrons. Okay, looks like this for water. There are 2 hydrogens, and they each bring 1 electron. Plus, there is 1 oxygen, and it's 6A, so it'll bring 6 valence electrons. So, and sometimes I'll get out my calculator to do this, honestly. So I get 2 plus 6, I'm like an 8 electrons. So 8 electrons is the pot of valence electrons that goes around my final Lewis structure. And can you see I do have 2, 4, 6, 8 on this final Lewis structure. Two pairs of these electrons, we have sigma, sigma, right? Because any single bond is sigma. And then I call them the dot dots. These right here are lone pair electrons. Lone pair electrons. A few things. Lone pair electrons actually give oxygen a complete octet, don't they? Without those, you would be in trouble. The other thing about lone pair electrons is they were part of the pot of valence electrons bought by those three atoms. So thou shalt use your entire pot, and thou shalt give everything a complete octet, right? Okay. So kind of like I said before, when you see Lewis structures or a Lewis structure like this, think of that O as representing the nucleus of the oxygen atom and all the non-valence electrons. Bond pairs are with solid lines. I shouldn't be saying dashes. Bond pairs are with a solid line. We talked about if you have a double bond, it's 2 lines. A triple bond is 3 lines, and each line represents a pair of electrons. So you guys told me 2 electrons, 4 electrons, and 6 electrons. It's possible, the reality is that oftentimes your pot of valence electrons are distributed so that you end up with these dot dots, these lone pair electrons. Like I said, even though I teased with kind of the north, south, east, and west, there is no significance. It's kind of interesting when I walk around and see your Lewis structures, the lab you're going to do Thursday. Some guys, I just kind of turn my head like, oh, you did that one upside down. And it really does not matter. Be a rebel. Okay. Obviously, when you draw on the board or when you draw on a piece of paper, it's flat. Okay? It is like just flat. But one of the things we'll be talking a little more about Wednesday and in Thursday's lab is that if you understand the spatial part of it, we'll talk about the spatial part of it. Honestly, the C2H6 spatially looks like this. So you can, and chemists do it all the time, because space is a player. You can take this flat and translate it to this in your brain. Okay? I've been playing around a little bit with the free apps. You can download the VR, virtual reality. I paid only like $20 for these. They're so cheap. But anyway, it's interesting. Okay. Spatially, it's kind of cool. Remember, this is the C2H4. It ends up being spatially, we don't care about these 2 electrons creating that secondary, that pi bond. So molecularly speaking, this thing it lies in a plane. It's flat. And I already called this my hot dog one. Okay. So yeah, you can kind of infer once you have the Lewis structure, and again we'll talk about that, you can kind of understand how that works. So let's look at a few Lewis structures. Ammonia, not to be confused with ammonium, which is NH4+1. Okay, this is the neutral molecule. It looks like this. So let's just for kicks kind of come up with a pot of valence electrons that we might have for these, 4 atoms. So it kind of looks like this. All right, so how many valence electrons does nitrogen bring to the table? Nope. So what's at the top? What group is it? 5, yep. So it brings 5 valence electrons. Yep. So it will bring 5. How many does hydrogen bring? Just 1. Yep, just 1 each. Yep. So the pot looks like this. I have 1 nitrogen atom. It brings 5 valence electrons. And I have 3 hydrogens, and they each bring 1 electron. So wow, I'm getting 8 again. And we'll talk on Thursday how you take kind of this information and get the final Lewis structure. But one of the checks for the final Lewis structure is this pot needs to show up somewhere here. Can you see we have 2, 4, 6, 8. We have 8 electrons. That's awesome. And the other check, of course, or another check is, if I look around my nitrogen, it's got 2, 4, 6, 8. It's got joint custody of 6 and real custody of 2. So 6 plus 2 is 8. Cool. Another thing we talked about was the whole reaching out or expected valence. So it's always 8 minus the group number. So for nitrogen, it's 5. Group number is 5. So its expected valence is 3. And so number of sigma bonds, 3. Number of pi bonds, none. So these are like checks. These are all checks, all smiley face checks that we made it right. Formaldehyde. So now we have these 4 atoms, and we'll talk again why it ends up being with this structure with carbon in the middle. I'll just go ahead and tell you it's going to be the one that's lowest electronegative. So if you find carbon and oxygen, remember electronegativity increases from left to right. So if we find carbon and oxygen, it increases from left to right. So oxygen's more electronegative, so it will be what we call the outsider terminal. So carbon is in the middle. Carbon, hydrogen, hydrogen, double bond oxygen, and yeah. So let's just double check that if this is the Lewis structure, so how many, that the pot of valence electrons must appear on the final Lewis structure. So how many electrons brought by each of those hydrogens? Just 1. How about carbon? How many valence electrons? I'm liking 4. How about oxygen? 6. Okay, so the pot looks like this. I have 2 for hydrogen times 1 valence electron each, plus 1 carbon, and there's 4 valence electrons for that, plus 1 oxygen, and there's 6 valence electrons for that. Get out my calculator. So I get 10, 12. Okay, so my pot is 12 electrons. So a check would be, do I have 12 electrons here? 2, 4, 6, 8, 10, 12. So that check works. Let's see, carbon, how many times does carbon expect to reach out? So it's 8 minus the group number 4. So 8 minus the group number 4 is 4. So it's reaching out 1, 2, 3, 4. It's reaching out 4 times. So if we pick on oxygen, does oxygen have a complete octet like that? 2, 4, 6, 8. Yep, it's got joint custody of 4, and it's got sole custody of 4. That was the word I was looking for, joint custody and sole custody. 4 plus 4 is 8. And carbon, of course, has a complete octet too. Is this the last one here? Okay. So this is one that you're supposed to be memorizing. Remember the halogens like chlorine form, oh my gosh, 4 oxyanions. This is the one with the least. So it ends in ITE and it has a hypo reward. So this is hypochlorite. So chlorine. So up here I'm going to go ahead and say, so how many valence electrons are on a chlorine atom? It's 7. Yep, it's just the group number. So 7 valence electrons. How many valence electrons are on oxygen? 6. Okay. Here in a minute, you're going to see me, or less than a minute, I'm going to kick in 1 for the charge. That charge, -1 specifically, means it means 1 extra electron. So here, I have 1 chlorine. It's 7 electrons. I have 1 oxygen, it's 6 electrons, and I have, plus, and I have 1 electron for the charge. So I got 7 plus 6 plus 1, I'm liking 14. And again, we'll talk more on Thursday. How do you know, a little bit on Wednesday. Thursday's lab should go again, good. So how do we know what to do with this plot of valence electrons? Well, let's just double check that I have 14. So I have 2, 4, 6, 8, 10, 12, 14. Perfect. Wow, they're overloaded with the, what, 3 pairs of lone pair electrons. But in doing that, do they each have a complete octet? Yep. I just think the concept of a covalent bond is just so awesome. Whenever you draw Lewis structures like this for something that's charged, a polyatomic ion, and I'll remind you of this, is you have to make sure you put the whole structure in brackets and then the charge outside. So just to kind of recap, atoms, as they form these sigma or pi bonds, do so and get complete octets, unless it's boron at wants 6, unless it's hydrogen at only wants 2, or unless it's an element that's greater than the third row or the third period, and then it can have expanded valence of 10 or 12. I will tell you on the test you won't have any expanded valence sort of deals. You might for homework though. Octet rule. Remember, octet means 8 rare gas configuration. It's all the same thing. So we've already kind of talked a little bit about the steps. We'll talk more on Thursday about this, but this is my pot. This is my pot of valence electrons. That's step number 1. We're down with that, right? The next is we're always going to put the one with the lowest electronegativity in the middle, and I'll remind you of that on Thursday, but in the case of carbon or oxygen, it was carbon, lower electronegative. Go ahead and draw on the preliminary Lewis structure with those primary bonds. Okay. Distribute any remaining electrons, or actually around the terminal atoms first, and if required, go ahead and swing in lone pair electrons to form a double bond. So I added to this, it says homework sets for part 7 will be due after we complete this week's lab. So you're looking at a week from today, because I thought, it shouldn't be Friday, it should be longer than that. Okay, so somewhere you need to remember. And then also on Thursday's lab, you'll have another opportunity to get 10 extra credit points for just doing like a worksheet. Okay.